We now have an idea of how we're going to find maxima and minima of multivariable functions. And the key we've established is that in order for us to have a critical point, we have to find such points where the partial derivative with respect to x of our function is equal to 0, and where the partial derivative with respect to y of our function is 0. And again, the motivation behind this is if you're sitting at a point that is either a max or a min. So let's just look at this downward opening paraboloid. In this situation, if we're standing at the top of this paraboloid, then it doesn't matter whether we look this way or whether we look, imagine this is looking towards our screen. It doesn't matter which way we look, our eye level will be horizontal with respect to the x-axis and simultaneously with respect to the y-axis. So let me go ahead and just overlay a pair of axes here. We'll say that this is our x-axis and that here is our y-axis. So I guess we should more precisely say that it doesn't matter whether you look along the x-axis or the y-axis, the eye level will always be parallel to each of those two axes. Now oftentimes, and it doesn't really matter how we label these, but a lot of times you'll see that these are switched when we're looking into that what we call the first octant, where x and y are positive. We often draw x going this way, but that's not necessarily required. So in this sense, because our eye level is flat, it's parallel to the x-axis, that implies that the derivative of that surface with respect to x will be 0. And since when we look along the y-axis, since our eye level will be parallel to the y-axis, the rate of change with respect to y will equal 0 as well. So here's just another example, and you can kind of see what that surface looks like. So you can kind of see that it almost appears as though 0, 0 is a minimum. And we would describe this in two ways. We could say that this is a relative minimum, meaning that it's a minimum relative to all the points surrounding it. But we can also indicate that this is also a global minimum. And global means that everywhere along that surface, any other point that you pick, anywhere along this surface, it appears that that's going to be the lowest of the lows. There are situations where you can have, both. Like let's imagine a surface like, something like this. And what we're seeing here is maybe this point right here represents a global minimum, meaning that across this entire surface, there is no point lower than that. And this is kind of a minimum, right? Because if you're walking along this surface right here and you make it down to this dip, you are at a minimum point, but it's relative to the point surrounding it, right? So between, let's say, here and here, that represents a minimum, but it's not global because there exists a lower minimum. And so that's the differentiation between global and relative. And then we'll also have another relative minimum right there. Okay, so for this function right here, we want to find its two partial derivatives. So f sub x of x comma y will be the derivative of e to the negative xy. I'll write it like this. The derivative with respect to x of e to the negative xy. Okay, well, how do we take the derivative of that? Well, we know that the derivative of something of the form e to the x, or e to the, if I took the derivative in brief calculus or our first calculus course of something like this, then I know that the derivative of e to the anything is e to the anything, but times the derivative of the stuff. So we have e to the stuff. It's not just e to the x, it's e to the 2x. And so when that's the case, we also have to take the derivative of the exponent, which will be 2 in this case. Now in our situation here, we're holding y as if it were constant, right? We're only looking at how does this function change when we change x. So y is acting like the 2 here. And so if we read this as the derivative with respect to x of e to the negative yx, and we think about this as our constant coefficient, then its derivative will still be e to the stuff. but times the derivative of the stuff. So the derivative of a constant times x is just the constant. So our final answer for the partial derivative with respect to x is negative y e to the negative yx. Now the partial with respect to y will be similar. We're going to take the derivative with respect to y of e to the negative xy. Now we're holding x constant, so negative x, this is a constant coefficient, and so the derivative of e to the stuff is e to the stuff times the derivative of that. So we have some constant times y, its derivative will just be the constant, and we'll be left with negative x e to the negative xy. So we have our two partial derivatives, f sub the derivative with respect to x of our function. We have the derivative with respect to y of our function. And now we need to set these equal to 0. So I am going to take negative y e to the negative yx, set it equal to 0. You don't necessarily need to write set above the equal sign. This is just makes it clear that we're doing the setting equal to. It's not always equal to 0. And then we can do the same thing for the partial with respect to y. Set it equal to 0. Okay, now this is a product of two quantities. So it's a product of this times this. And whenever you multiply two quantities together, the only way that product will be 0 is if one or the other is 0. So for example, if I tell you some number times some number equals 0, what you can guarantee is that A equals 0 or B equals 0. One of those has to be true. Now this is kind of like our A, this is kind of like our B. So this means that negative y equals 0 or e to the negative yx equals 0. Now you might be looking at that and thinking, oh, wow, how am I going to find the value of, how am I going to solve this equation here? Well, the good news is that if you raise a base to any power, when we think of exponential functions that have negative exponents, they decay, but they never actually reach 0. So this curve will actually never reach 0. So that means that this equation has no solutions. Okay, so raising e to a negative power or even a positive power is not going to cause it to ever reach 0. Okay, and that means that if negative y equals 0, that means that y equals 0. And now in the second equation, same kind of principle here, either this equals 0 or this equals 0. Again, e to the negative yx will never equal 0, but negative x can be 0. How can negative x be 0? Well, the only way a negative of a number can be 0 is if that number itself is equal to 0. Or you can think about this as dividing both sides by negative 1. And then, of course, the second condition would be that e to the negative yx equals 0, but that's not possible. So we obtain y equals 0, x equals 0 as our critical point. So our critical point is the point x, y, z equals 0, 0. Well, wait a minute, what's the z value for that? Well, to get the z value of it, I have to go back to my original function, because this function, remember, tells me at any given xy pair, what's the size of z. F of xy is another way of saying z. So I'm just going to evaluate f of 0, 0. So this is going to be f of 0, 0. And if I plug in 0 for x and y into this equation here, I'll have e to the 0 power, which is 1. So that represents a local minimum. It's at the point 0, 0, 1. And from the graph, we can see that this is a relative minimum. But how do I know that? How do I know that without looking at the graph? A lot of times, technologically speaking, plotting three variable functions, computers still have a hard time rendering, shouldn't say have a hard time rendering, but they often don't render things the way they should actually appear. So we have to have some way of checking if that's a relative minimum or not. Or maybe it's a relative maximum. Well, there are three situations that we have to investigate. One which we haven't seen before, called a saddle point. But this is called the second derivative test. And to determine if a relative extremum being it could be a min, a max, or this thing that we don't understand yet called a saddle point, it occurs at a critical point C comma D. So first of all, in our case, C comma D is the point 0 comma 0. So here's what we have to do. We have to compute this quantity called D at our point 0, 0. And we have to compute the right-hand side by, well, what's this f sub xx thing and what's this f sub yy thing? Well, f sub xx is the derivative. F sub xx of xy is the second derivative with respect to x. Okay, so how do we do that? Well, we've already established that f sub x, that the first derivative, is equal to negative y e to the negative yx. And so now what we have to do is just take the derivative of this thing again. So the second derivative is really just taking the derivative of the derivative. And since we already have that, we just have to take the derivative of this guy. Remember that negative y, that's a constant. This is also a constant. So when we take its derivative, any constant multipliers, like if I took the derivative of 3e to the 3x, its derivative would be 3 times e to the 3x, so 3 times e to the stuff times the derivative of the stuff, which would just give us 9e to the 3x. So in this situation, we'll have negative y e to the negative yx times the derivative of that exponent. Well, y is a constant, so that's just going to be multiplied by negative y. And so I see that I have a factor of negative y here, a factor of negative y here, so this will be y squared e to the negative yx. And the partial with second derivative with respect to y, we know that f sub y is equal to negative x e to the negative yx. So to take its second derivative, we just have to take the derivative of the first derivative. So here, in a similar sense, x is constant. X is being treated as a constant. So its derivative will be negative x e to the negative yx times the derivative of that. Well, that right there is the same thing as negative xy. So negative x is a constant. And so that'll be multiplied by negative x, which gives me negative x times negative x is positive x squared e to the negative yx. Now this little weird guy here, f sub xy, is the derivative of f sub x. We take the derivative of f sub x. This is the first thing we took the derivative with respect to. Now we're going to take the derivative of that guy with respect to y. I know that seems strange. This is called the mixed partial derivative. And it's not our objective here to get into the theory of what this means or where this comes from. There's quite a bit of mathematics going on behind the scenes. We just need to know how to execute it. So what are we going to do? Well, we're going to take our f sub x at x comma y is equal to negative y e to the negative yx. And now we have to take its derivative with respect to y. Okay, well that means that now I have a product of two factors involving y. Okay, so I'm going to write this like this. I see I have a product of a function of y times another function of y. All right, so I want to take the derivative of this with respect to y. So because it's a product of two factors, both of which involve y, I have to use the product rule. And the product rule says that if I identify something as, I'll call this F, and I'll call this, whoops, I don't want to call that whole thing F, I just want to call this F, and I call this G, then the product rule states that the derivative of a product will equal F prime G, the derivative of F times G, plus the derivative of G times F. Well, we already know that the derivative of F, that the derivative of negative y with respect to y will be negative 1. G is just the original function, e to the negative xy, plus the derivative of e to the negative xy with respect to y. That's what we're taking the derivative with respect to. We already know what that is. We don't have to do it again. That's equal to this up here. That's going to be negative x e to the negative yx. That's my g prime. My f is the original function here, which is negative y. All right, so we have all the pieces that we need to compute our d-test value, and we'll talk about in just a moment what that looks like. But so far I have all the partial derivatives that I need. F sub yy, F sub xx right here at the top, and now it's going to be a matter of just plugging in our critical point into all three of these equations. So this says, first calculate d of 0, 0. That's our critical point. So this is going to be f sub xx, the second derivative of f with respect to x, evaluated at our point 0, 0, times f sub yy, evaluated at our point 0, 0, minus the square of f sub xy, evaluated at our critical point 0, 0. So that's going to be this value squared. All right. So if I plug in 0 in for x and y here, well, let's see. 0 squared is 0 times e to the 0, that's 0 times 1. That's going to be 0. And it doesn't really matter what f sub yy is because it's going to be 0 times something, but let's just go ahead and do it anyway. Well, it's going to be 0 squared times e to the 0, that's going to be 0, minus our f sub xy evaluated at 0, 0. So if I plug in 0 for x and y here, that will give me a negative 1 times 1 is negative 1. And then here I'll have 0 times something. This whole term will be 0. So I'll get negative 1 plus 0, which is just negative 1. So all I'm doing there is just plugging in the value 0, 0 into this equation here. And then we need to square that. So we get 0 minus negative 1 squared is 1, and we get a d value of negative 1. Okay, now what do we do with that? Well, first of all, we have to look at the value of d. There are a couple of different conditions here. If the d value is bigger than 0, then we need to check this. We need to check something else. The second condition says if d is greater than 0, then we need to check something else. And if d is less than 0, which it is, right? This is less than 0. That's negative. So we would say that f has a saddle point at that location. So 0, 0, 1, our critical point, is a saddle point. So it's not a minimum, it's not a maximum, it's called a saddle point. Well, what does that mean? I'll show you. So imagine a Pringle potato chip. You've probably seen these before. They sort of have these double curves. So imagine this point right here, which is sort of right in the center. Now, it almost looks like a horse's saddle. Like you could put your legs right here. This is a leg, and then your other leg down here. I'm not very good at drawing legs. And then the person sits here, right? Like this. So that would be kind of like a saddle. All right. A Pringle potato chip is like a saddle. And what we mean by that is that in one direction, that point right there represents a maximum. That's the peak of this curve right there. However, if you look at it from that was from front to back, if we look at it from left to right, we see that it's actually a minimum. So a saddle point is a point that is a minimum in one direction and a maximum in the other. And so now we've fully classified this critical point as a saddle point. Now, consequently, that's not necessarily a good thing if you're trying to maximize or minimize, because a saddle point is kind of the combination of the two. So it's not the biggest value and it's not the smallest value. Hence, we give it the name a saddle point.